All right, so we're going to do a few things. I want to do the clerical work that I normally do here in a second. But before we get there, I kind of need to start a lab. So in your packet, okay, I need you guys to find the determination of the specific heat capacity of a bolt. We are just going to fill this in very quickly. All right, good. All right, and I'll take attendance again at the end. All right, so I'm going to start this little lab, and then we're going to do it. Now, this math gets tough. So as long as you stay with me, we're going to be okay. This is as tough as the math gets in this unit, though, okay? So let's do this. So the first thing, before we talk about the week schedule and all that kind of good stuff like I normally do, is we're just going to start this lab because it takes 5 minutes until we can do it. So what I have here is a bolt, and it's simply a bolt on a string. So you guys can all see here, just a bolt on a string. We'll talk more about what we're doing with this bolt on a string in a second. But the first thing I want to do is I want to get the mass of this bolt on a string. So I put it on the scale. It's 38.62 grams. So if you would please take a look right in the middle here where it says mass of the bolt, 38.62. Okay. And then all I'm going to do is, you see I have some boiling water here. Beautiful. I'm going to take my bolt on a string and I'm just going to put it in the boiling water. Okay. That's all I'm going to do. I'm going to turn it over so it's not touching the side. I want it right in the middle of the water. All right. Now, it's 9:13. I'm going to boil that bolt for 5 minutes. That's all we got to know right now. And then we're going to do some math here in a second. Okay. So we'll come back to our little bolt here in a second. Let's talk. First thing I want to talk about is the schedule that we have coming up here. The schedule that we have. So you guys know that we are in week 11 of this year. Week 11 is here at the beginning of November. Today we're going to talk about the bolt lab. Perfect. Tomorrow we don't have school. It is election day, so you don't have anything to do tomorrow. Then on Wednesday, we're going to practice this again because this is very tough. Thursday, we have a lab. I'm going to try to figure out, I would like to burn food. We burn food every year. It's not exactly COVID friendly, but we're going to work tomorrow during our work day to see if we can. I want to try to pull it off, so we're going to try. And then your quiz on Friday, though, will have to do with these calculations, and this stuff can be a little challenging, so you want to make sure you're here. Then for week 12, we're going to talk about states of matter. We're going to start to do some review, and you guys will have a unit test next Friday. Everything thermochem, okay? We're talking entropy, spontaneity, endoexothermic, Q calculations, all that stuff. Okay, and we'll review before that, so no worries. But that's kind of where we're headed. I like to make sure everybody knows where we're headed. So the only other thing that I would like to review is all the Q equals MC delta T stuff. And you don't have this in your notes, and that's okay. Let's just talk about it. We know, to refresh, Q is equal to MC delta T. Okay. We also know that Q is the quantity of heat energy or joules. Okay. Then we know that M is mass, and that's in grams. And we know the specific heat capacity is joules per gram degree Celsius. And we know that the delta T is change in temperature. We all agree with that. We took a quiz on it last week. We feel good. All I have to add on in order for you to successfully do this lab today is one thing. We know the law of conservation of energy says energy cannot be created or destroyed. So whatever energy is gained by something, okay, energy gained is equal to the energy lost by something else, okay? So at the end of the day, if you can say the amount of energy something gained is equal to the amount of energy something lost, and Q is equal to MC delta T, it should make sense mathematically that the mass and the C and the delta T of the substance that gained is equal to the mass, the C, and the delta T of the substance that lost. Now, this is really ambiguous right now, but this is what I need in your head when we do this lab, okay? All right, so we've been boiling for about 4 minutes. Let's get this lab going. So today, on your worksheet, it says I have a bolt. And what I want to know about this bolt is I want to know the specific heat capacity of this bolt. So it says you need a standard apparatus, check. Bolt, got it. Electronic balance, check. Styrofoam cups, I have right here. Thermometer, check. And tap water. Now what you would have done is you would have done these steps. It says prepare a hot water bath, check. Measure the mass of the bolt, got that. An empty cup. So I'm going to re-zero this. Put my empty cups on there. And we're looking at 9.17 grams. So let's write this here. 9.17 grams. Place the bolt inside 4 or 5. I don't think he's here today. That's where he usually is. Okay. All right. So you have put the bolt in boiling water, heat it for 5 minutes. We're working on that. Then it says get 60 mils of tap water. Oh, I don't have my graduated cylinder. 60 mils of tap water and put it into the cup. Here we go. All right. Now, when I put my 60 milliliters of tap water in here, the cups with the tap water says it's 69.33 grams. I need everybody to grab a calculator here, even if it's on your phone. I'll grab mine. How do I know how much water I just put in there mass-wise? If the cups were 19.1 grams and the cups with the tap water in it are 69.33 grams, what do I do with those numbers to figure out how much water is in there? How did you do that? Subtracted? Okay, so let's all do this together because I'm running the math with you today. 69.33 minus 9.17. Did we all get 60.16 grams of water in there? All right, so let's write this really big. 60.16 grams. This is a very important number. This is my M for H2O. Let's write there. That's how much water mass I have. What do we see here? This is my M for my bolt. Remember, we took the mass of it before we got started, and now it's been boiling. The last thing that I need to do, I'm take a thermometer. I'm going to turn it on. I'm going to put it inside of this water, and we're going to figure out the initial temperature of the water. All right. We're looking at 23.4 degrees. Now, before I do this little lab, I want you to think about what's going to happen. When you do a lab, you want to predict. It says right here, obtain the temperature of the cool tap water. We did that. Quickly transfer the bolt to the tap water and get the temperature when it is done. Is this bolt going to be hotter or colder than the tap water when I throw it in there? It's going to be hotter, right? What do you think is going to happen when I take a hot bolt and put it in cold water? It's going to make the temperature do what? It's going to go up. We all can see that coming, correct? So we expect it to go up from 23.4 to something else, correct? All right, let's get it going. So I'm going to take my bolt here. It's in the boiling water. Move that guy out of the way. 1, 2, 3, go. And the temperature of my water should go up. And then I'll turn that off so we can all hear each other better with the masks and such. Okay. All right. So currently, which direction is thermal energy flowing? It's going from my bolt into the water, correct? Raising the temperature, and we look like we're kind of settled here at 28.5 degrees Celsius. Okay, so now I want you to think back to what we just talked about. So you're not writing anything, we're just going back here. So what happened when we put this all together? The bolt lost energy and the water gained energy. We agree with that. Bolt was hot, lost energy. Water was cold, gained energy. Because of the law of conservation of energy, and you'll see this on your practice questions, because of the law of conservation of energy, those Q's have to be the same. So that means if the question said, I want to know the specific heat capacity of the bolt. I want to know how many joules it takes for each gram to heat up. So if I want to find the C of the bolt, is there a way that I could calculate how much Q the water gained and set that equal to the what was lost? And you have the mass, and we'll talk about delta T, and we're finding C. So we're trying to do what's called a QQ calculation. I know the Q that gained. I can figure out how something about what was lost. Okay, so let's do this together. Are you ready? And then I'm going to have you practice it by yourself because this stuff is tough. The last thing we really have to think about before you get into the math. Why do you think I boiled that bolt? I wanted to get it hot. How hot is water when it boils? Anybody have any idea? What does water boil at? There's a number. Is it 0 degrees Celsius? No, what do you think? 100 degrees Celsius. So if this water boils at 100 degrees Celsius and it never changes, and I put that bolt in there for 5 minutes, if you were a betting person, what do you think the temperature of that bolt was before I chucked it into this water? 100 degrees, right? So right here, the initial bolt temperature before we mixed it was 100 degrees Celsius because it was boiled. Look up in your data table, what was the initial temperature of the water? Perfect. 23.4. Then we put them together and they met where? At what temperature did they both come to at the end? 28.5. Let's write that there. Perfect. If anybody at home has any questions on how I'm getting this, let me know. Okay. All right. Now, we need a couple delta T's, if you will. Everybody has a very easy time saying, well, I know that the bolt went from 23.4 to 28.5. What do I do with these numbers to get a delta? Yes, you subtract. So let's take it. Everybody grab a calculator. You can probably do it in your head, but we'll do it together here. 28.5 minus initial temperature, final temperature, 23.4. How many degrees did the water warm up? Okay, 5.1. Does anybody not understand how we got that? We're just not talking on a Monday to me. All right, go over there. I gotcha. Okay. Now, the second part of this wants to know how much the metal cooled down. Remember, they have different specific heat capacities, so it's harder, okay, to get the water to heat up. That's why it didn't heat up as much. But let's see how much the metal cooled down. It went from 100 to 28.5. Enter. Hopefully you got that. The delta T of the metal was 71.5. Does everybody get that? Okay. So we're just figuring out some stuff here. Now, this is my delta T of my metal. This is my delta T of my water. This is my mass of my metal bolt. Maybe I should write bolt here. And this is my mass of my water. There is one thing that you need to know about water, and I didn't write it on here. What is the C value? What is the specific heat capacity for water? You know, you memorize it, you got it?
I got it.
Thank you.
Nobody?
Nobody?
Oh, let's
We're not talking today. We're not talking to me today. 4.
4.
Point. There you go. See, you guys know. I haven't seen you a week and now you're scared. All right, let's see. H2O is equal to 4.18. That is something you'll need to have in your mind. Remember, we said you just got to know that number.
I'm pretty sure we had.
Yeah, they did. They all got 100%. They know that number.
I know.
We're just not saying it. But thanks, Mr. Chan, for starting that off. All right. So now, thinking about the conversation we just had here a second ago, if I know how much energy is gained, I can set that equal to how much energy is lost because of the law of conservation of energy. So all you have to do is now fill in the information that you know. And I am trying to put a question mark right here. I want to know the specific heat capacity of the bolt. Or you can put X or C or whatever you want. Okay? So let's just drag these numbers down. A little participation will go a long way. What is the mass of the water? The mass of my water. That was my cups. You got it. You got the math. You actually did that math for me there. 60.16 grams. Mass of my water. We just said, we can try this again. What is the C value for water? 4.18. Thank you. I see some of you already have this all filled in. I love it. What was the delta T of your tap water? Perfect. 5.1. What was the mass of my bolt? 38.62. The question that we said at the very beginning is, what is the specific heat capacity of the bolt? And that is my C value. So I'm going to leave that alone. We'll make that the X if you would like. And the delta T of the bolt was? You got it. Now, let's talk about how we must solve this. Grab our calculators here. I'm going to multiply all three things together on the right side, or the left side, excuse me. 60.16 times 4.18 times 5.1 should be a big number. Oh, yeah, 1,200. 1,282.49. Is that what everybody got? Okay. That's how much energy was gained by the water. All right. Now, on the other side, we are going to multiply. We have an X there. So, but let's just do 38.62 times 71.5. So I got 2,761.33. These numbers turned out pretty. And we'll call that with C on it. Okay, because the specific heat capacity is still over there. Does anybody not understand algebraically how I got here? All right, so now, this is, if I told you, hey, 4 is equal to 2x, how would you solve for x? Divide both sides by 2, right? So we're doing the same thing. 1,200 is equal to 2,700c. So what I'm going to do is I'm going to take, and we're going to divide both sides by the 27. So 2761.33. It looks weird. It's going to give you a very small number, but that's okay. 1282.49 divided by 2761.33 equals, what number did you get? It was a small guy, less than 1. The specific heat capacity of the bolt that we calculated was what? 0.4, and if I round, 6. Awesome. Thank you. Remember, the unit for specific heat capacity is the weird one. It's joules per gram degree Celsius. Okay? Now, I slugged you through that math, okay? That was tough. We were going to practice this a whole bunch more a little bit today and tomorrow. Or, excuse me, you're not here tomorrow. Wednesday. But what I want you guys to do, first of all, let's see how close we were, okay? These bolts are made of iron. And iron's specific heat capacity is 0.449, so 0.45 joules per gram degree Celsius. So were we close? Oh, heavens, yes, we were close. That's awesome. We did really good there, okay? But the main idea that I need you to walk away with, because you have to be able to do these calculations by Friday, is the energy gained by something, or the Q, is always equal to the energy lost by something else. And if you boil something, that means that it's going to start at 100 degrees. So we're going to do this kind of piecey. I usually have you do your lecture questions at the end. What I want you to do right now is I would like for you to do your lecture questions right now. Then I want you to try to run the calculations again by yourself. You can either do like a different color. I was going to copy a whole nother one, but I didn't want to waste another piece of paper. So maybe that was my bad. But here is some fresh data. I would like for everyone by the end of the period to be able to tell me the specific heat capacity of this bolt with this data. Okay. So I'm going to come around. I want you to answer the 3 lecture questions to make sure everybody gets their points in for today. And those of you at home, answer the 3 lecture questions. Then I want you to, and you can do this right alongside the data we did together. If you had cups that were 9.01 grams, and then the water was 67.19 grams, and the bolt was 38.49, and it took the temperature from 23.6 to 28.7 degrees, what is the C value for this bolt? Okay, and I'll give the answer at the end. So hopefully everybody come around, checking in, seeing how we're doing. Any questions on the lecture question? All right, we're going to go over this in just a minute, so you guys can have a little bit of time to yourselves at the end. All right, are you ready? Let's do this together. Here we go. All right, so right on your same page, you were adding the same data, okay, but we just went ahead and we added some new data to it, okay? So if your cups were 9.01 and your cups of the water were 67.19, what do? You need to subtract those, correct? And hopefully everybody in here got the number 58.18 somewhere. Perfect. Then you need to say, all right, the bolt was boiled and it started at 100. My water started at 23.6. And then they came together at 28.7. Perfect. I love it. You guys are doing great. This is actually really tough. You guys are making it look easy. My temperature went from 23.6 to 28.7 is a delta T of, again, 5.1 for my water. My bolt went from 100 to 28.7 was a delta T of 71.3. Yes. We know that the C value of H2O is 4.18. Let's take everything we need now and put it down in here. The mass of the water was 58.18. The mass of, or my C of my tap water is 4.18, and that water warmed up 5.1 degrees. That's how much energy my water gained. That is equal to the amount of energy that my bolt lost. So I can say the bolt was 38.49. I'm looking for C, and my bolt cooled down 71.3 degrees. Did everybody get that in there? Beautiful. Okay. Then when you multiply them together, 58 times 4.18 times 5.1, You got about 1,240.28. 38.49 times 71.3 C would be 2,744.34 C. Feeling good on that? Nice. You guys are doing great. Now, to finish this off, this is the side with X. So I divide both sides by 2744.34. That gets X by itself. And when I divide 1,240.28 by 2744.34, you get again 0.45 joules per gram degree Celsius, which is, again, I gave you the sample data for another iron bolt. Okay, so this is the intro to this math. If you kind of look in the packet on Wednesday, we're going to do a couple different types of metals. So you'll have to tell me the specific heat capacity of those different metals when we chuck them into water. Okay, so this is what your quiz will look like on Friday. The math is tough, but doable. Okay, as long as you know the law of conservation of energy and you know Q is equal to MC delta T, okay, you can do these labs easy. And we would have done like 3 of these labs, but yay for COVID. Okay, so you guys did great. I'm going to give you the last 5 minutes to yourselves. Thank you very, very much. Everybody make sure they got their lecture questions in. Those of you at home, if you want to head out, you can, but make sure you do your lecture questions. If you have not, take the next 5 minutes to do so. Okay, thank you guys.